Hello everybody, my name is Hunter Ream and I'm going to be talking to you about Generating Functionology by Herbert Wilf. We're going to specifically be covering section 2.2, the calculus of formal ordinary power series. So the things that I want to cover today in particular, we will be outlining 5 rules for ordinary power series generating functions. Okay, the acronym OPSGF. I guess we can say plural. And then we will go over a few examples. So here's a definition that we're going to need, because I'm going to be using some notation that's sort of strange. It's used in Herbert Wilf's book. Here, we'll write it down. The symbol F, and then a bijection symbol with OPS written over the top of it, ordinary power series. And then a sequence next to it. Let's say the sequence is a sub n, ranging from 0 to infinity. This symbol means that F is the ordinary power series for this sequence. And that kind of makes sense just by the symbols, but in particular it means that F is equal to the sum from n equals 0 to infinity of a sub n x to the n. So it's what you'd expect the power series to be. Now the first rule is this, rule 1. And like I said, my goal is to go over these 5 rules and give a couple examples. How I'm going to do that is I'm going to explain the rule first, and then we're going to do some examples to really solidify the rule. So if F is the ordinary power series generating function for the sequence a sub n, then for h greater than 0, I'll try to distinguish my h's from n's by having the long stick on the left-hand side of it. So for h greater than 0, strictly greater than 0, a sub n plus h, the sequence from 0 to infinity, will have the ordinary power series that is written as f minus a sub 0 minus dot 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 minus a sub h minus 1 x to the h minus 1. And that's what we're doing. We're actually subtracting off the first, so there's more to this a little bit, but the first thing that we're going to do is we're going to subtract off the first h minus 1 terms. And that's actually, if you look at, here I'll use my pointer, this piece right here, we start at 0. So when I plug in 0 for n, then that means we're starting at the h. The first term is a sub h. So we want to have the first term in our power series, our ordinary generating function, to be, well, a sub h. So let's subtract off all the first h minus 1 terms. But we can't just stop there, because we also need to have the x's have the correct powers on them. And in order to do that, we're going to need to divide by x to the h. And then that'll perfectly give us the ordinary power series for this. And this rule is a shifting rule. So that means if we ever have a sequence, we can actually determine, if we ever have a sequence and its generating function, we can determine the generating function for the shifted sequence as well. So let's do an example of this. This is, so the Fibonacci sequence has the recurrence well, maybe you know this, we'll say that the Fibonacci sequence is denoted by f sub n, but the recurrence is f sub n plus 2 is equal to f sub n plus 1 plus f sub n, where the first term, f sub 0, or say maybe the 0th term, is 0, and the first term is 1. And this is going to be true for all n greater than or equal to 0. So suppose that little f is the ordinary power series generating function for the Fibonacci sequence. Then the recurrence relation turns into, let's see this. So this shift rule actually makes our life a lot easier, because now we don't need to go through everything that we went through before. If you watch some of my previous videos, there was a ton of algebra involved in trying to figure this out. But now, if we have the generating function and we have a recurrence relation, then we can actually just come up with a power series like this, or yeah, an ordinary power series. Let's look at this. So this first term here, shifted by 2, well, if f is our ordinary power series for fn, then we know this fn, well, that's going to just turn into f. Okay, well, we know that. That's pretty straightforward. But now we even know how to tackle these shifted terms as well. So f sub n plus 2, well, we have to go up to our rule here. So all this says is that, well, we know when h is equal to 2 here, when h is 2, then the ordinary power series is going to look like f minus a sub 0, which in our case is f sub 0, which is going to be equal to 0. And we also need to subtract off f sub 1, which is 1. And then we need to divide by x squared. And that's it for that side. Oh, sorry, this 1 times x. And then on the right-hand side, we have an f sub n plus 1, so it's a single shift when h is equal to 1. So this is going to be f minus 0 all over x to the 1 by our rule number 1, and then just plus f. Now, that turns into, just simply writing it, getting rid of all the zeros, f minus x all over x squared is equal to f over x plus f. So now from there you can just easily solve for f and get your generating function right away. And that's really, really useful. I'm not going to solve for the generating function, but I believe that you guys could do this. So that's pretty nice. It seems now that when we're given a recurrence relation, which is typically, probably always given to us in terms of the sequence given by a shift, then we can actually just use this rule in order to come up with a generating function from that recurrence relation. Okay, so now what I'm going to do is I'm going to go to rule number 2. So let's see rule number 2. Rule 2. So again, if f is the ordinary power series for a sub n, and p is a polynomial, probably given in terms of n, but you know, it could be anything, then p of x df is the ordinary power series generating function for Pn a sub n from 0 to infinity. Now, this notation right here, P of x df, is strange, and I have not explained what that means, but I'm about to, and I don't want you to just get intimidated by the notation, because I will explain this. This d, though, just so you understand, I haven't defined what it is at all. This is going to be our differential operator, and x is as x would be in the power series in f, but what this says is that we will be differentiating something. In particular, we'll probably be differentiating f. But I want to go over an example to really drive this home so that we can make sense of this. So just bear with me. Let's try this. If f is the ordinary power series generating function for a sub n, the question would be, a good question, is what is the ordinary power series for n, a sub n? So all it's doing is moving a single n. We're just saying, instead of just having our regular sequence, we want to multiply by the index at each term. So by rule 2, this is really what rule 2 is going to be used for here, is by rule 2, by multiplying just by an n here, it is actually, well, n is just a polynomial. It is a polynomial in n, right? It's just a single, it's n, but it's actually, we can view this as a polynomial in n. So we're gonna view it just like that, and we're gonna use rule 2. We see that by rule 2, our ordinary power series, n a sub n, has the ordinary power series that is, well, instead of writing p, I'm just going to write x d f, because I'm putting xd into the function n. So it just forces me to write just xd. There's no decorations on that. Just xdf. Now, what does that mean? What that means is that I will be taking f and what I know about f, we're going to differentiate it, and then multiply by x. Okay, so we're going to try to get used to this. And the reason for this, what is actually happening here, is since f is equal to n equals 0 to infinity of a sub n x to the n, then df, since I'm just saying df is just differentiate f, is equal to n equals 0 to infinity of n a n x to the n minus 1. I'm just differentiating this term by term. And so x df, this is notation really, which means that we just have, well, I'm going to take df and multiply through by x, we get n a sub n x to the n, which is exactly the power series generating function then for n a sub n, which is what we wanted. So this is enough right here. This x df, that's enough for us. If we had an f, we would actually be able to explicitly come up with the formula for this n a sub n. And that's really nice. So that's really the reasoning for the rule. I mean, that's really kind of what's going on there. Now notice that this doesn't really need to stop here. So what if let's do another example. We're going to still say that f is, if f, so we'll say let f be the ordinary power series for a sub n. But instead of just finding n a sub n, n a sub n, we want to find the ordinary power series for n squared a sub n. And all this is going to do is force us to use this XD process twice. And this means, all we're going to do is, well, we can actually just look at rule 2 and notice that, well, we're just going to be putting in XD into n squared, so it's going to be XD squared. Here's the solution. We'll say that n squared an has the ordinary power series, which is xd squared quantity f by rule 2. But this would actually make sense. If we work it out, this is because well, we already know that xdf is equal to n equals 0 to infinity of n a sub n x to the n. And now if I differentiate this again and multiply by x again, then, well, first off, then let's differentiate it. dx df would be equal to, well, differentiating this, right? So n equals 0 to infinity of n squared a sub n x to the n minus 1. So we're only off by this single x. So then multiplying by x, so xd f would give us exactly what we want. Oops. N squared a sub n x to the n. So that's the power series generating function we want. Now we write that as what I have written first, but we write this as xd squared f, because we just do it twice. So that's nice. And this is where this is coming from. And we already know that power series extend linearly, so we can split this up by addition. So this is actually the way we're going to treat all polynomials. This is a nice rule for all polynomials. And so really, whenever you have a sequence already, and there is a polynomial, and you're trying to find the generating function for that sequence, with now just a polynomial sitting in front of it in terms of n, well, we can do that. Okay, so that sums up rule number 2. Let's go to a new page. Oops. So rule 3 is if we have f as the ordinary power series a sub n from 0 to infinity, and g being the ordinary power series, let's say for b sub n, then fg, we can multiply these power series together and get that this is actually going to be for the series. This is going to be the generating function for the series of sums from r equals 0 to n, a sub r, b sub n minus r. And so that's the rule. And this kind of feels like we're just multiplying two generating functions together and getting a sequence, whereas the other rules were, when we're given a sequence, we were trying to come up with a generating function. So it feels a little different, but remember, we're trying to develop a calculus for these generating functions. So we want to be able to multiply generating functions. And that's exactly what we're doing here. Also, if h, say, I guess we'll bring it down here. If h is the ordinary power series for a different sequence, c sub n, let's say, then fgh is the ordinary, we'll redo that, is the ordinary power series for all the sums where each of these add up to n. of a sub r, b sub s, c sub t, all multiplied together, ranging from n equals 0 to infinity. So that's the rule. And this next rule, let's say rule number 4, is related entirely to this rule. And that's the reason I'm not going to give an example of that right away. You'll see an example in a second of why this is useful. But rule number 4 tells us that, well, let's let f be as such, be the ordinary power series for a sub n equals 0 to infinity. And let k be a positive integer. Then f to the k, raising this ordinary power series to a positive integer, well, that's going to be the ordinary power series for the sum where all of these will add up to n, all the indices will add up to n, just multiplying all of these terms together. So it's going to be a bunch of partial sums, and I think that's kind of cool. Let's see how this is actually used in practice. This is cool. So let f and k be the number of ways. The number of ways to write n as an ordered, I'm going to underline that, ordered sum of k non-negative integers. And our goal is going to be to find an ordinary power series for this sequence. Okay, so we want to find an ordinary power series. And here's the solution. We'll know this, I guess. Find the generating function. So the solution goes like this. Recall, and this is just by the geometric series, recall that the sequence 1 will have the ordinary power series of 1 over 1 minus x. So this notation is getting useful now, right? This is the ordinary power series. Thus, by rule 4, 1 over 1 minus x to the k will be the power series, the ordinary power series, for, well, the sum from, n1 plus n2 plus ... nk of, well, these are all of the indices of our sequence of ones. And all this is saying is that each time, so this is when it's adding up to n, of 1 times ... times 1. Okay, well, each one of these here are it's just going to be 1 times 1, k times, but that's not going to matter because we're just going to get a 1 here, but we're also going to contribute a 1 every single time one of these sums exists. And that'll actually collect every single one of these sums, and it'll tell us how many of them there are. And so that's exactly by rule 4, so that's really cool. So this right here is equal to, this sequence is equal to our f of n comma k. So we actually have this right here. This right here is the ordinary power series generating function for this sequence. And that was really quick. It's a really slick rule, and it's really useful in my opinion. So here's the last rule. And, of course, it's Rule 5. We said there were 5 rules. So Rule 5 says this. If f is the ordinary power series for a sub n, 0 to infinity, then taking f and dividing it by 1 over x is the ordinary power series for really the partial sums of this sequence. The partial sums, where n is ranging from 0 to infinity, which is super neat. And to prove this, we actually need to understand what it means to multiply two generating functions together. Well, we're not going to explicitly prove this, but we're going to at least make sense of it through this example. We're just going to say, notice that if we take f and we multiply it by 1 over 1 minus x, which is exactly what I'm doing on the left-hand side right here in the rule, well, that's the same as multiplying these two generating functions together. If f is for some ak, as we would say, we're going to take that generating function, we're going to multiply it by the generating function that's just generated by all ones, x to the k. And in order to do this by our rule, by Rule 3, this is the ordinary power series for the sum from k equals 0 to n of ak times the n minus kth term of our sort of trivial sequence, which is just always going to be 1, so I'm not even going to write it. So it's really just the partial sums here from n equals 0 to infinity. So it is indeed the partial sums, and that's pretty cool. As an example of this, I mean, there's a ton of things that are counted like this. Let's only do one example here on the harmonic numbers. So the harmonic numbers are this. The harmonic numbers h sub n. We'll note that this sequence starts at 1 and goes to infinity. You'll see why. Are defined by h sub n, which is equal to 1 plus 1 over 2 plus dot 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 plus 1 over n. So by Rule 5, we already see that each one of these terms is going to be a partial sum of the sequence 1 over n. So by Rule 5, the generating function for this sequence h sub n is given by f over 1 minus x if f is the OP ordinary power series for 1 over n, from 1 to infinity. So now this problem is reduced to just finding the ordinary power series for 1 over n, and in order to do that, we see that df for this would be equal to, well, I guess this isn't obvious, but we'll just see that f would be equal to x to the n over n, from n equals 1 to infinity. So df, just differentiating that, bringing the n down, subtracting 1 from that, would end up being n equals 0 of x to the n. So that's just going to be, which means df, I mean this is the, using our power series, or sorry, our geometric series, it's just 1 over 1 minus x. So we know that when we differentiate this f, we're doing calculus, right? When we differentiate this f, we get 1 over x. Thus, or 1 over 1 minus x. Thus, f, if we can integrate this, we see that f would end up being equal to negative log of 1 over x. Because we know when we differentiate this, then we of course get that. So that's pretty cool. We're actually doing calculus with this stuff. So we actually found the ordinary power series. So this sum from n equals 1 to infinity of h sub n x to the n is equal to 1 over 1 minus x, let's make that a little better, times log of 1 over 1 minus x. And I just applied the log rule of bringing this negative as an exponent on here, okay? But yeah, so this is our power series generating function. We just use this last rule to find it. So this is really useful. I hope you enjoyed that, and thank you for listening.